Bismillahirrahmanirrahim. This video is from Electrical Machines, Induction Motors, and here we'll be discussing example 6.23 from 5th edition, which is almost same like example 7.19 from 4th edition of Mr. Chapman's book. And for this, actually, a student had requested here some difficulty. I have just a little confusion in 7.19 where R2 is to be found. And then he has given this snapshot. I tried it by your method, but I did not get the answer. Can you just make me understand this? So primarily, I want to make him and all other students who have doubt to understand this question. So before we go to the question, these are the two per phase equivalent circuit of an induction motor. And this part is actually the stator part and this is the rotor part. And same here. If the difference between the diagrams are this part here is R2 by S written, and here it is R2 separately written and then R2 1 minus S over S separately written. And if you add these two, it will be actually R2 over S. Now let's compare this with the help of the power diagram that we have studied in earlier videos. This is the air gap power and this is the power converted and this output power. So as I was mentioning, this part is the stator part and which is linked with the air gap power. And now this one accounts for all power crossing the air gap. So after this, any power crossing is represented by this resistance or this resistance take care of the powers ahead of PAG. Whereas here, this takes care of the rotor copper loss and this one takes care of the remaining P converted actually. Now they represent exact same physical quantity, but they show it in broken down differently. Now this diagram generally is used when the input current, we need to find input current or we need to find input power or power factor or torque. Whereas the second diagram is preferred when you have to calculate the rotor copper loss one and converted mechanical power this one. Now as we go, we will be eliminating this resistance RC, which is the rotor copper resistance, because this value is very negligible as compared to XM. This is 7.19 and this is 6.23 example. Question is same except for the values here. It is 50 HP, 75 HP, and the values of the resistances and inductances, they are different. So we'll be using this, but if you want to solve for this example, just follow the same technique. One more thing, I'll just be solving part A of the question, and then I hope that you follow and you can do the part B, C, D. But if you have difficulty, let me know so I can make another video. So this is going to be already very long video. So part A only will find. Now to find the rotor resistance R2, there are several formulas which can be used. But primarily I'll be using this formula. So this is easier to follow. And to find or to use this formula, we need to find the value of T induced. For that, we'll use this formula here. P induced is P converted over omega m. So these two formulas we'll be using to find R2. Now this, as I mentioned, is the further simplified diagram. We have removed R, RC. We start with the voltage. The 460 volt given here is actually line to line voltage. So we convert into phase voltage divided by under root 3. So the phase voltage will be approximately 266 volt. And then we'll plug in the other values of X and R, etc. Okay, and as we mentioned, these are the two formulas that we'll be following. So first of all, from here, you can see that he has used V Thevenin and R Thevenin. So let's calculate that for this circuit. And from this point, we divide the circuit into two parts. This part we'll find the Thevenin equivalent, and then this will be using as load. So this will be the Thevenin circuit, V Thevenin, Z Thevenin. We're separating the load. And now, first of all, we'll calculate the Z Thevenin. And you know, for Z Thevenin, we short circuit the input voltage, short circuited. And now you can calculate it parallel. This branch is in parallel with this branch. So Z Thevenin can be calculated as shown here. Plugging in the values. All these values now will plug, and solving, we will get the answer in rectangular form. And if you want, you can also find it in or convert it into polar form. We don't need it here. We'll be just using this value. And so in our equivalent circuit, Z Thevenin will now be, this is R Thevenin and this is X Thevenin. Now, let me show you a technique. In your calculator, you can very easily solve this by going into the complex mode. So let me just clear this. From here, you have to select 2 for complex mode. So we are going 2. Now you can see complex is written. So we are in complex mode now. And we'll select this fraction option here. So we write the denominator, bracket 18. J, for J we write I. So this is I. So we press this. So 18I, bracket close. Then next bracket 0.058 plus J 0.32, so 0.32I, bracket close. So numerator we have entered. Now coming on to the denominator, 0.058 plus bracket 0.32 plus 18, bracket close, and now we'll enter this J, which is I here, I. So we have entered all the values. Go ahead, press equal sign. So you can see the answer is 0.0559, and the imaginary part is 0.314546. So this is how you can easily calculate the value. If you want to find it in complex mode or the polar form, simply you press Shift and 2 for complex, and then 3 for R theta. So you can find this value 0.319 and angle 79.9. But we don't need it here. So we have found the R Thevenin. Now we'll find V Thevenin. And by voltage division rule, total voltage divided by total resistance and multiplied by the resistance across, we are going to find it. So this, or we can just write it at the top and this there. Same thing, plug in the values, V Thevenin. Now here we need to convert it into polar. So this is the polar form 261.35, and we can write to be approximately 261, but this is small compared to this, and the angle is almost zero, so we will not write the angle. So our V Thevenin is 261 volt. So the Thevenin part we have done. Now let's see the torque part or the output power. In the question it is given 75 horsepower is the power. So that means this is the output power here. So 70 HP rating given in the motor nameplate is the shaft output power or the delivered mechanical power. Now, if losses are neglected, the induced torque in a motor is equal to the load torque. So we know this 75 is the power here, and this is representing in a way the torque load. And if we neglect these losses, then torque load will be equal to torque induced, because power out will be equal to power converted. The output power is 75 HP and slip is 1.2 HP. So the induced torque, which is also equal to load torque, is P induced is P converted over omega. You can see this formula from here. T will be P over omega, P converted omega or P out over omega, same thing. So 75 HP, and we convert HP into wattage, multiply by 746 and divided by omega m. We don't know omega m as yet. This is the mechanical shaft speed in radians per second. So we have to calculate this. Okay, so this is the question. How do you find this? This diagram is representing the mechanical parts of the motor. This is the rotor part. This is stator part. We can calculate the speed of the induced magnetic field, and from there we can find the rotor speed. So let's see how. These are the parameters given. So to find the synchronous speed or speed of the magnetic field here, we'll use this formula 120 F over P. F is given to be 60 Hertz, and there are 4 poles. So synchronous speed is 1800 revolutions per minute. We can convert into radians per second also by writing omega synchronous now, multiplied by 2 pi and divided by 60. It is 188.5 radians per second. So this is the synchronous speed. We are here. Now the slip comes into play to find the rotor speed. So this will be slightly reduced from the stator speed, and it will be reduced by the amount of slip. So this is the formula that is used, that the mechanical speed is 1 minus slip divided by the synchronous speed. Also in terms of radians, we can say that omega m is 1 minus s omega sync. We know the value of s, which is 1.2%, that is 0.012. Omega sync we have calculated 188. Therefore, the mechanical speed in radians per second is 186.23. So now we can plug it in here to find induced torque. So T induced is approximately 300.4 Newton meter. So we have calculated all these parameters. Now we can plug in into the equation for T induced. This we have found. V Thevenin we have found 261, and all other parameters we already know from here. So plugging in, and now if we multiply these two, it will be 56625. This one will be giving this value. And now we will open this bracket terms. So from here, actually, we are doing further simplification, dividing by 56625. So it will be 1 here, it will be 3.6 here. Now, cross multiply, then opening this bracket. And further simplifying, we actually want to find a quadratic equation from here. So we're just rearranging the terms. This is in quadratic form now. I hope you can follow from here. And from here, we can find the two roots. Solving the quadratic equation, R2 over S is 3.341 and 0.14. Now this also you can easily solve by your calculator. Let me show you. Calculator, now we have to change the mode here. Equation mode 5 and 3 is for the quadratic equation. And now it is asking the coefficient for the first part. So the coefficient here is 1. So we'll put 1 equal sign. Coefficient of second part is minus 3.488. So minus 3.488 equal sign. And the third part is 0.49. 0.9 equal sign. So we have entered all the value. Now we'll press equal again. So we get the first value 3.341, 3.341. And the second root, we press equal sign again. So the second root is 0.1466. So we have found R2 over S. Now we know the value of S, which is 0.12. So we multiply with that to get R2. So from here, R2 can be written as this 0.040 and 0.017. We'll rename them as R2 single dash and R2 double dash. Now the question is which one to select. Let's see. These were the two R's, two values of R, and the rule that we'll follow is that select R2 such that the slip of full load should be less than the slip of the maximum torque. And what does that mean is, let's see from this diagram, this is the torque, speed and slip curve. And you can see this is the maximum point, maximum torque. And the slip at this point is called maximum slip. So this is maximum slip. And the question has given a rated motor torque. And for that torque, the slip was given to be 1.2%. So this will be called a full load slip. So full load slip has to be less than the maximum slip or the maximum torque slip. So we need to calculate slip maximum for both these values. This is the formula for slip given in the book. We can further simplify this to this value. That is, we can eliminate R Thevenin, and the reason is generally R Thevenin, you say this is R Thevenin, is a very, very small as compared to the sum of this and this. And therefore, R Thevenin, when neglected, then this square will cut with the under root, so we'll get this formula. So we'll be using this formula to find the two maximum slips. So this was the formula. So R maximum for R2, this was the R2 dash. This for this is 0.0025. And for the second R, that is R2 double dash, it is 0.057. And we know the full load slip given in the question is 1.2%, which is 0.012. So now we can compare the three and to apply this rule. So you can see 0.025 is less than 0.012 is less than 0.057. And these were actually, this is due to R2 single dash, and this is due to R2 double dash, and this is the full load. Therefore, this one is valid. This is following this rule. So we'll take this. That means R2 double dash is the valid value. So we take R2 double dash is equal to 0.040 ohm is equal to R2 as the valid answer. I hope you have been able to follow this. Please let me know through your comments. Thank you.